Our first speaker, Dr. Ramon Schifano, who is an associate professor at the Institute of Physics of the Polish Academy of Science. He is an expert in Schottky contacts and electrical characterization of zinc oxide using capacitance spectroscopy and galvanometric techniques. He received his diplomas from the University in Florence and a PhD from the University in Oslo, where he also worked as a postdoc. After stays in Pretoria and Linköping University, he found his base in Warsaw, Poland. Zurich Instruments have a long-term relationships with Ramon, dating back to 2015, when he was one of the first users of the MFIA. And we are grateful that among the fruits of this relationship, we can name 2 application notes on DLTS. Currently, Dr. Schifano is studying the defects of zinc oxide and its alloys. The alloys may have a potential to be used in solar cells. It is my great honor to invite you all for a talk from Dr. Ramon Schifano entitled DLTS and Thermal Admittance Spectroscopy, 2 complementary techniques to characterize defects in semiconductors. Before I pass on the mic to Ramon, let me remind you to use the Q&A box and send us questions to the talk during and after. Ramon, welcome, and the floor is yours.
Thank you very much, Magda, for the nice introduction. So I will start this the presentation. And so, one moment. Okay, so as Magda said, so title of this presentation is the Deep Level Transient Spectroscopy and Thermal Admittance Spectroscopy, 2 complementary techniques to characterize defects in semiconductors. And I'm working at the Institute of Physics, Polish Academy of Science. My name is Ramon Schifano. So the purpose of this presentation is to, since it's the first presentation of this webinar, so we decided with team that it was good to have a kind of introductory presentation. So I will go through 2 techniques that can be easily, let's say, implemented using in parallel, the DLTS and TAS. Starting from essentially the basic concepts, then I will go a bit ahead and I will put some more advanced things here and there. I hope that in this way I made this presentation interesting for the varied audience that I think is attending this seminar. So at the end, I will summarize what essentially are the main differences in between the 2 techniques in one slide, in a way that this is essentially the take-home message of this presentation. So what are the plus and the minus, the pros and the cons of these 2 techniques? And both of them can be realized with each LC meter that you have in your laboratory, and we realize it with MFI, for example. So to start with, what are these 2 techniques used for? So they are based on capacitance measurements, and are used essentially for determining what are the fingerprints of the electrical active defects in the semiconductors that are here, that is the capsule cross-section and the position of the defect into the band gap. What you need is some kind of rectifying junction. It can be a Schottky contact. It can be N plus or P, N plus P or P plus N junction. Essentially, what you need is that the pitted region is extending mainly in the part of the semiconductor that you want to characterize. Now I will move one step back, in a sense that I would like to remind you something. So, whatever samples you are using, it can be a vertical structure, it can be a horizontal structure where you have the only contact that is placed on the same side where you have Schottky, or it can be the N plus or P plus layer. Well, this is the equivalent circuit of your device. While what the emitter that you are using is expecting, is assuming that is attached to its terminal, is essentially a capacitor in parallel with a resistor. So here I put the admittance corresponding to the real device. As you see, it's much more complicated than what the emitter is expecting to have connected to its terminals. And this admittance expression is reducing to this one in case that these conditions are satisfied. So in case that essentially, from a physical point of view, the voltage drop on the series resistance, it's negligible or much smaller than the voltage drop on the resistance that is modeling your the resistive part of the depleted region, contribution of the depleted region, and the impedance, this condition here, and the impedance of relative to the capacitance of the depleted region, this condition here. This condition here is generally, let's say, satisfied by standard devices, while this condition is sometimes not satisfied. So you have to play with the probing frequency that you use for measuring the capacitance in a way that this condition can be satisfied. And this is essentially the reason why we then at some point we choose to work with MFI, because it was possible to, and this is what we did, implemented a program that is permits to make DLTS by using essentially whatever frequency that you want to use, obviously compatible with the device that you are characterizing. If this condition are satisfied, you are able at least to know, let's say, what you are getting out from the emitter is what essentially you would like to measure, and you can even estimate what is the accuracy of the measurement that you are doing based on this comparison. So I added one slide just to mention and promote this method that was first suggested by Werner on how to extract the series resistance, because this is, as I said, the first parameter that you should know about your device before going ahead and doing DLTS, TS, or other more advanced characterization of the material. So what generally people are doing, if they are making some kind of fitting of the forward part of the current versus voltage characteristic, essentially this equation here, what you can do, and what Werner showed is a bit more accurate, is, for example, if you take this equation here, you differentiate both of them, both sides for the voltage that's applied, and you divide both sides by the current. What you get is what you would expect is the G over E, the conductance divided by the current versus the conductance. You have a linear behavior. By doing a linear fit, you can extract series resistance and the identity factor. So now we are essentially, we are getting to the core of the presentation. So we know how to, at least I show you an additional method to calculate RS, the series resistance. So then we go back to the previous slides and we know essentially what is the approximation that we are doing and what is the frequency range that we should use for our measurement. And then the question is, should I do DLTS or TAS? Or should I do both of them? What can I expect from these techniques? To make things a bit more simple, I will focus on majority carrier traps, on N-type semiconductors. So essentially, I will focus on defects that are interacting with the conduction band, okay? So the defect will be charged if the Fermi level is above the defect, will be empty if the Fermi level is below. And now I will go through a bit of DLTS, a bit more in detail, and thermometer spectroscopy. So to start with DLTS, I guess that all of you knows the principle. I will just remind you of this slide. So you start with I'm considering here a Schottky diode case. So you start with the junction that is reverse biased. We are in situation 1. Then you apply a pulse in the forward direction, situation 2, charge the drops. Then the pulse is released, and we go back to the initial situation. So what is happening is that the electrons are emitted from the drops. This is the equation that is governing the emission of electrons from the drops. The time constant is the coefficient, the emission rate. Okay, one over the emission rate. Sorry. So this is how and what you are doing. Meanwhile, you are monitoring the capacitance. So and you are acquiring the capacitance transient. So this is the general expression for the capacitance transient. And I would like to point you out that you have this geometrical factor that sometimes in the literature, for example, is not mentioned. They give already some approximate formulas. So you have this expression here. And this expression here has also behind this expression here there is an approximation that the trap concentration has to be much lower than the donor concentration, at least 1 order of magnitude lower. It's a dilution approximation. So if you acquire the transient at different temperatures, so where the emission rate is changing, and you then do a Arrhenius plot where you plot the emission rate versus temperature, then you can extract the two characteristics, parameters of the defect. It is the upper capsule cross section and the positioning that band depth actually is enthalpic energy. So the point here is to somehow acquire the defects versus while changing the temperature and somehow create this DLTS spectra. As mentioned by Magdalena, so the first paper from Lang, where he was the first paper on DLTS, so he used this approach here, the boxcar approach, for essentially extracting the DLTS spectra from the acquired transient. So that is based on sampling the transient in two different times, with respect to when the pulse is released. So when the transient is very low, you have, and you take the difference in different points. The difference is essentially 0. Then when the transient starts to be resonant with the rate window, then you have a maximum. Then when the transient is too fast, then you again have a minimum in the DLTS spectra. So essentially, from a mathematical point of view, what you are doing and how you are constructing really the DLTS spectra is that you have your transient, you multiply it by the weighting function, and you do an integral over the time interval on which you are acquiring the transient. The choice of the weight function is in a way that you have the DLTS spectra when the emission rate is essentially resonant with the window that is selected by the weighting function. So there are a lot of weighting functions that are possible, that have been proposed, that you find in the literature. I just take 2 examples here. One is beside the boxcar that was mentioned 2 slides before. One is the lock-in, that is essentially GS2, where you take the transient, you split it in 2. The first part you multiply by -1, the second part by +1, and you sum up what you are getting. Then you have the GS4 and subsequent ones that have been first proposed by Statov in this paper. Actually, if you look at this paper, the coefficient that he's doing and this giving in this original paper with Statov are wrong. These are correct ones. So what is done in this case is you take the time interval, the transient, split it in 4 equal parts, and again you multiply by, in this case, this coefficient in the sum of it. So to show you a bit more in detail what is happening, I took a case of palladium sodium concept to zinc oxide and did some measurements. and the transient has been post-processed according to lock-in weighting function and according to the GS4. This is just to show you what you would expect, let's say, what you expect in different cases, okay? So as you see here, what is happening is you work with lock-in, so it's less sensitive to the noise. So you can work with lock-in when you have, for example, low signal to noise ratios. While when you work with the GS4, you have increased sensitivity. So the width of the peak is less, so you can resolve more peaks. On the other hand, you have more, let's say, noise. So you have this has been done by using the same transient. So here the signal to noise ratio is the same. So there are two other points. So this is generally what you know from the literature. So there are other 2 points that generally are not so stressed in the literature. First of all, you can have, for example, in this case, you have a false root. So you see, let's say, what you would maybe consider like a minority color related peak. Actually, this is not a minority related peak. It's simply because of the mathematics that you are doing. Secondly, if you use then what is coming out from GS4 for calculating your concentration of traps, as you can see here, simply because of noise, the GS4 is not able to pick up the maximum of this peak here. The peak here is lower than what you are getting, a little bit lower than what you are getting from lock-in. So these are things that you should take into account, and these are in general what is, let's say, the problems that you can face when you do this kind of post-processing of the graph. The time constant that you are able to resolve by using ordinary DLTS, so that you apply the transient scanning, is something like in the factor 10. Start with the factor 5. I would say that this is a bit an optimistic value. The factor 10 is more realistic for what is possible to achieve in, let's say, in laboratory. Another approach that you can use is to essentially, if you start from your transient, is to invert by numerical routines the transient expression to get a spectral transient, spectral density of the transient. So how the emission coefficient are varying versus frequency. In this way, you can achieve time constant ratios that are of order 2, much better. So to show you what this, let's say, what here is it's happening, I took again the same sample as before. I did the Laplace DLTS, so that means that essentially you don't acquire the transients during scanning the temperature, but you fix the temperature, you try to keep it as much as stable as possible, and you acquire as much as the transient you need to have achieve a good signal to noise ratio. In this case, 500, 1000, much more. So what you see here is that actually what we were seeing that was only one peak in by using the lock-in and the GS4 weighting function actually are 2 peaks. And the difference in the emission rate between the 2 peaks is slightly more than a factor 2. Again, also in this case, you have a different numerical routine that can be used for extracting, for doing the inverse Laplace transform. These are 3 of them. All 3 they show that there are 2 peaks. So this is actually what they are all of them consistent. So I would like to end up the story. So then this is the Arrhenius plot. So emission rate divided by over 2 of the temperature, and here are the versus 1000 over t, and these are the points extracted. So the red points are extracted by Laplace DLTS, and relative to the main peak that we saw, to this peak here, while this one from Laplace DLTS relative to the smaller peak, the shoulder towards higher emission rates, emission rates with higher frequencies. Plus, here there are points related to the, what is coming out from nuclear. So the difference in between two peaks is essentially you have peaks, two defects that have activation energy that is pretty similar. The big difference is in terms of what is the apparent capture cross-section. It is more than 1 order magnitude difference in between the two defects. And this one has large cross-section. So I don't want, obviously, this is not a conference presentation, so I don't want to go more in detail on this without what is called in zinc oxide literature, what is labeled as E3 prime level. What I would like to stress you here, because this can be interesting for some of you, is that essentially if you put this activation energy and this apparent capture cross-section, you go back and you evaluate what is the emission rate for this kind of defects, then you end up with an emission rate that is in the 100 kilohertz megahertz values at room temperature. That means that if you do CD measurement at room temperature, then you will pick up this defect, in the sense that this defect will respond to your CD measurements, and it will, so essentially you cannot compare your CD measurement. Generally, you are doing some kind of CD measurements just to extract the carrier concentration. But what you are getting out from CD measurements will not what is coming out, for example, from Hall measurements. Because this defect will not be thermally activated at room temperature. So if you do DC measurement like Hall measurement, it will not be there, or the contribution will be very small, while it will essentially respond to CD measurement. I will come back to this point later on when I show you some results concerning TAS. So now I'm closing this part concerning DLTS, and I'm going to TAS to show you essentially, again, I will do the same as I did in the case of DLTS. So I will start with some basic concepts, and then I'll show you some examples, what, let's say, you should be careful, what can be done and cannot be done in the case of TAS, and then I will conclude. So we go back now to our Schottky contact, and we go back to the same figure. What you're doing during TAS is actually you monitor the capacitance and the conductance. I will show you in the next slide why the conductance. During essentially you do a temperature scan. Okay. So you keep your reverse bias constant, and you do a temperature scan. So the basic principle behind TAS is that you would expect something that is happening because you change temperature, emission rate is changing. So when the emission rate is fast enough with respect to the problem frequency, then the defect will charge and the charge all the time. Okay. Then at some point you will start not to essentially this defect will not be able to follow the problem signal anymore. So essentially it will you will have some kind of delay. Okay, so you will not be able to follow the AC voltage you are applying. And here it's important to point two big difference in between TAS and DLTS. So first of all, you don't do any pulsing towards the forward biasing. So that means that it's much more difficult that you have minority carrier injection. So in this case, only majority carriers are involved. In general, you can assume. Okay, it depends a bit, but let's say it's the technique is less prone to this kind of effect. Second thing, in general, what is happening is that you are probing something that is at the end of the related region. So in this case, in the case of DLTS, you are charging defect in this region. So in this region, you have large electric fields. that can affect the emission rate. While at the end of the depleted region, you are in a region where the electric field is much more intense, and it means that the electric field effects are more can be considered negligible in this case. So to understand, let's say, what is the physics behind of TAS, before going to let's say the formulas that are essentially governing the steps and drops that you see in peaks and drops that you see in capacitance and conductance, I would like you to give you some ideas what is essentially the physics behind it. So what you do, you pulse the essentially now let's think that we are monitoring the charge, okay, that is inside and outside of our junction by applying a voltage, okay, so the angular frequency of our probing voltage. Then what, as I was mentioning before, so you would expect some kind of delay, okay, phase shift here. This is depending on the temperature, simply because at some point the defect will not be able to follow anymore your probing signal. So if you take the real part, it's what we are interested in, and then you go to, let's say, you solve this, so you go in solve this cosine. So what you are finding is that you have a part that is in phase, that is decreasing with increasing delay, and a part that is out of phase, that is actually increasing the more after the delay. Okay, now we are actually, what we are interested in impedance, so we have actually voltage divided by the current, so this will be actually the in phase, the phase part, the part that is in phase, so this will be conductance part, while this will be the out of phase part, so the capacitance part. So you would expect something happening also to the conductor. From a more formal point of view, if you solve the Poisson equation and go, let's say you really do this in a numerical point of view, analytical point of view, sorry, what you are getting is that the drop in capacitance is essentially proportional to this quantity here. And there are two things here to point out that are important. First of all, you have again this region between the traps concentration and the main donor concentration. However, this ratio here, as you see, in this case, there is no limitation in the ratio. So you can work with also TAS spectra can be used also in the case that you have a higher concentration of traps than the main donor. So this is a difference with respect to DLTS. Plus, you have this dependence here from the geometrical factor, and you have this what I'm calling cantilever effect. So essentially, as you can see here, the more you go farther from your particular junction from Schottky contact from the metal semiconductor junction, the more this x1 will get equal to xd, because lambda, the place where the difference between xd and where the Fermi level is crossing the level that we are interested in, the trap level that we are interested in, sorry, the energy position of the trap level is constant. So this will get, the more you're getting farther in your junction, will get closer to 1. So this signal will get closer to 0. So the step will be smaller and smaller. So you lose in sensitivity the more you are getting deeper in your junction. Considering the conductance, what you're doing in TAS generally, you're not putting the conductance, but you're putting the conductance divided by the angular frequency that is used to probe your junction. So in this case, what you expect is something like this. So you expect what is, let's say, what is analyzing this equation. So you expect actually a peak in conductance, and that peak is occurring when the probing frequencies is equal to this omega 0 that is related, something like a more or less a factor pi general, larger than factor pi, to the emission rate. So again, when you see the peak, that means that you are factor pi, let's say, from the sorry, the emission rate is a factor pi equal to the problem frequency. And again, what you can do an Arrhenius plot, and from the Arrhenius plot extract what is the position of the defect into the magnet activation energy, plus also the effective capsular cross-section. I didn't put it here because it's a bit more complicated, it's a bit more cumbersome in case of TAS spectra, because actually what you have is you have a dependence of it's not as straightforward like in the case of DLTS. You have some kind of geometrical factor also in this case to extract the apparent capture cross-section. So now I went quite fast through what is the theory behind the TAS. I would like to I'm making some examples so you can get some clue how to extract and what are actually the difference in between theory and experimental results, and some clue how this data are processed. So here you can see this is capacitance versus temperature measurements, and in this case are conductance divided by the probing frequencies versus temperature. I took this, these are quite old data of mine actually, because these are data that there are a lot of things that are were happening in this case. So I thought that this, for a pedagogical point of view, this was the best thing to show in this case. So first of all, let's focus on what is the, what if you go down in temperature, what is the first peak in conductance that we observe. So we observe this peak here. As you see here, this peak has actually, if you remember what I was showing in the previous slide, you would expect essentially this peak is constant height equal to 1/2 of the step in capacitance. This is actually not the case. You have a slight increase versus higher temperature of the peak height, and this is due to the background that is increasing. And what generally is seen, increase the temperature you are measuring, the diodes generally are increase the reverse current is increasing, and this is what you see here. I would like you to have a look on this graph here. As you can see, there is the capacitance drop that was according to TAS theory, what you would expect. But the capacitance is also slightly dropping down also before the step in capacitance. And this is it can be, for example, related to what I was mentioning before. When if you have interfacial states, well, the TAS measurements, because of this cantilever effect that I was mentioning before, they are very TAS measurements are very sensitive. So this could be, for example, if you want to be sure that these are interfacial states, what you should do TAS measurements at higher, let's say, reverse voltages, and see if this curve is flattening out. This is actually what was done in this case. So again, you do your Arrhenius plot from where the half of the height of the capacitance, so you can extract the temperature, and you can do then the Arrhenius plot, or from the peak in where the peak in the conductance divided by the probing frequency is occurring. You can extract the temperature, and then you can do your Arrhenius plot and extract the activation energy and upper capture cross-section. Okay, so we are back, this is this E3 level, and here you can see what I was mentioning before. So if you do temperature, if you do CD measurement at room temperature, so we are around here at 230 degrees C, essentially you will pick up essentially most of the signal from coming up from E3. So this is what I was mentioning before. So defects that are not that deep and have apparent capture cross-section, then they can respond. The response is quite large here in logarithmic scale. So it's a large response here. So you can let's say miss if you interpret this as carrier concentration. Actually, you are much the value that you are extracting is much larger than the actual value. Another interesting feature of this samples was that this second peak, or lower in temperature, has a clearly temperature dependent behavior. You see here, this is quite essentially the main freezing out peak here is a shoulder, while the main peak is a quite large peak, and then this contribution is decreasing, and you end up here is the reverse. So the freezing out peak is the main peak, and here you have a shoulder related to this. This behavior cannot be attributed to any background effect, like in this case here. So it is related to the fact that you have increase in the leakage current because you increase the temperature. This is pointing to some kind of thermally activated process. So again, from the position, you can extract do the Arrhenius plot, extract the activation energy for this defect. It was around 100 MeV in this case. So what the point here is, well, we did at the time, we did the DLTS measurement on the samples as well. And for example, we did ordinary DLTS, and this peak was not present in this case. Plus, so you have a peak that is thermally activated, you have a peak that is not present in DLTS. So this, what can be? And here let's say we came up with this interpretation of the data. And the point is here again, I will go through this a bit in detail, but not too much, just because let's say we wanted to focus on the difference between DLTS and TAS, not on let's say the characteristic of the defect. So assume that you have a defect that has let's say you can charge and decharge, but also it can capture an electron, overcome a barrier if it is thermal energy is enough, capture a second electron and go to a deeper state. But then in this case, so I have a kind of metastable defect, negative U defect. And in this case, if you are fast enough, so if you do, for example, TAS, in this case, TAS was enough, then you can charge and discharge this defect without that essentially it's able to to overcome the barrier and do this transition here. On the other hand, if you do ordinary DLTS, where you charge, let's say, the pulsing times, or let's say generally you do something like 100 milliseconds or something like this, then you give time, plus you're working in a different temperature range in this case. Well, you give time to the defect to cross this plus because of a higher temperature range, it has a higher thermal energy. Give time to the defect to overcome the barrier, do this transition, and so you will not see it by DLTS. So the message here is obviously DLTS, you can see metastable state by DLTS. I'm not saying this, that is not possible. But what this generally do is either you go for fast DLTS, where you use very fast pulses and you acquire very fast transients, or you have to prepare the defect before by doing some kind of, for example, illumination, something like this. So let's say the reason why I put this example here is to fix in your mind that here we are probing the defect with the faster frequencies, because we are using the AC voltage is using for probing the defect. Why in the case of the DLTS we are looking to emission rates that are slower generally. So the last, let's say, the difference between TAS and this, I will conclude this presentation of the timing time. Last difference is the freezing out, and so we are back to our, in this case, it's a circular presentation. We are back to where we started for, so the equivalent circuit of our device. If you consider now that we are interested in this quantity and we have freeze out all the other defects, so in this case, G over V is equal to 0. We are above, we have the peak, and we are now after the peak. So this quantity is 0. So essentially, the depleted region will be essentially, you can model it as a single capacitor. But what is happening when the electrons are falling down on the donors, okay, when we start to have the freeze out? Well, now the bulk actually is getting more and more resistant. Okay, and what is happening is actually this, what is, let's say, what you have below the detector region, the bulk of the samples, then you have to model it by something like this. So then, if you consider you solve this equivalence circuit and you calculate U over V and you calculate the capacitance, what you're finding out is that actually is something very nice. That again you have that what you expect, and for G over V is a peak. And the peak of intensity, that is the intensity delta C over 2, exactly like in the case of ordinary trans peaks, plus what is the condition for which, at which this peak is occurring is this one here. So where T is the total resistance due to this resistors here. So what is then you consider the resistances related to the resistivity is one over the mobility and the carrier concentration that is related to Fermi level position to the position of the defect into reactivation energy of the defect into the band gap. Then again you can construct an Arrhenius plot. And from the Arrhenius plot, if you know how the mobility is behaving in that temperature interval, you can extract the activation energy for the defect. So we are going back to our data. We are talking now about this bit here. And so from the position of the defect, considering that in this region here, if you do all measurements, this is the temperature dependence of the mobility in this temperature range, you can do your Arrhenius plot and you can extract the activation energy that is around 50 MeV in this case. So I'm essentially closing, and I'm closing with what I promised you. So it's a summary of what, let's say, the main differences in between DLTS and TAS. So what should be remembered, TAS is some kind of volume measurements. That is then generally what you do for avoiding to deal with this geometrical factor to work with the larger reverse biases. While in the case of TAS, you have the reverse. You would like to have to work with reverse biases that are not junction not so much reverse biased. Okay, so that can be applied also to the junction that are not that good. In case of DLTS, you have this dilution limit, plus you have electric field where the traps are emitting. This is not the case, or generally is not the case in the case of TAS measurements. Plus what I mentioned in the last slides. So you have, let's say, you're working in different mission rate regimes here. In case of the DLTS, it's generally slower, faster. In case of TAS, this can be useful in case that you have some effect changing their configuration. In addition, TAS it can be useful for detecting what is, let's say, the main donor in your defect. So I will end up with this presentation. I thank you for your attention. I hope that this presentation was interesting for all of you. And I end up with some literature here. Just since Tim told me that this presentation will be on maybe online at some point with some literature that can be useful for you, for if you want to go a bit more in detail in what I was saying here. So thank you for your attention once more.